All right, let's get started with the last session. So this is the session on algorithms, and our first speaker today will be Yicheng Yang from Beijing Institute of Technology, and he'll be telling us about effective resistance computation on graphs.
Thank you. My name is Yang Yicheng from Beijing Institute of Technology, and I'm going to talk about our recent work, the improved algorithms for effective resistance computation on graphs. So effective resistance is a basic metric on graphs. So we model the graph as an electrical network, and each edge has an edge resistance which is proportional to 1 over the edge weight. Then we send a unit current flows in through S, flows in through the node S, and flows out through the node T, and we count the effective resistance between S and T. This is denoted by RGST. So the computation of effective resistance has various applications in graph algorithms and graph learning. For example, the graph specification problem, the max flow computation, and recently understanding the overscorching phenomenon in graph neural networks. So I'm going to provide some basic definitions relevant to the effective resistance. So we consider an undirected, unweighted, or constant bounded weight graph G with n vertices and m edges. Then we have the adjacency matrix, we have the diagonal degree matrix, and we have the Laplacian matrix, and also Laplacian pseudo-inverse. So the ST, effective resistance, is formally defined by RGST equals ES minus ET transpose times the Laplacian pseudo-inverse times ES minus ET, where ES and ET are the one-hot vector that only takes value 1 at coordinate S or T and 0 otherwise. So the problem now is that given the two nodes S and T, can we locally approximate the ST effective resistance? And in this work, we follow the previous results by the ITCS 2019 paper and the KDD 2021 paper, which represents the Laplacian pseudo-inverse by the Taylor expansion on the lazy probability transition matrix, where here we denote P quota equals 1/2 times the identity matrix plus AD minus 1 as the lazy probability transition matrix. Then based on this representation, we can simply random walk some graphs to locally approximate the ST effective resistance. So now we can define the L step truncation of the effective resistance, which is truncated the Taylor expansion of the lazy probability transition matrix at step L. So we can easily prove that when G is an expander, L equals O quota 1 is enough for a good approximation for the effective resistance. So there are the following results by the Paris paper, which says when G is an expander graph, then there exists an 1 over epsilon square time algorithm that epsilon approximates the ST effective resistance. So now the problem is that we want to do better than 1 over epsilon square. So our first result says there exists an square d, root d over epsilon time algorithm that epsilon approximates the ST effective resistance for the expander graph G, where d equals the minimum of the degree of S and degree of T. This implies the improvement in terms of epsilon, but at a higher cost but higher relies on the degree of the graph. So the techniques of this paper is inspired by the Patreon computation, where we combine the deterministic search algorithm with the random walk sampling. So we can define the PLU, the vector, as 1/2 times the L step truncation of the Taylor expansion of the lazy probability transition matrix. Then we can compute the four terms, and by the definition of the L truncation ST effective resistance, this is the linear combination of these four terms. So we just need to focus on the approximation on these four terms. And next, we introduce our deterministic part of the algorithm, where we denote it as the coordinate gradient descent, also known as push. So we maintain a sequence of sparse residue vectors R0, R1 to RL, we denote QLU as the approximation of the vector PLU, and we set a threshold Rmax. And the algorithm goes like the following. Initially, we define the residual vector R0 as 1/2 times EU, and we define the residual vector for the following steps RK equals 0, and we define the approximation QLU to be 0, and we define K to be 0. Next, for each round K, and we search each coordinate W with RKW larger than the threshold Rmax over L squared times the degree of W. Then we perform the following push operations. We update the QLU at coordinate W by RKW. We update the residue of the next round RK plus 1 by RKW times PQ times EW, and we set RKW to 0. And after the operations, we turn to the next round and repeat. And finally, we return the approximation QLU and the residues R0, R1 to RL. And so our algorithm for computing, for approximating the value PLST is by combining the deterministic algorithm with random walk sampling. So for the first step, we use the deterministic algorithm CGD from S to closely approximate the vector PLS. Then for the next step, we perform random walk from T to refine the approximation PLST at the specific coordinate T. So the observation is that the residues by the deterministic algorithm R0, R1 to RL are exactly the expectations by random walks. And then the variance of the random walk, so therefore the variance of the random walk is controlled by the threshold Rmax. So the operations by the deterministic part is bounded by OQ 1 over Rmax, and the operations by the random walks is bounded by OQ Rmax D over epsilon square. By setting a suitable threshold Rmax, then we can obtain an OQ root D over epsilon time algorithm, which implies an improvement over the approximation parameter epsilon. So for the next problem is the lower bound for the local effective resistance approximation. So our second result says, given the parameter epsilon, then there exists an expander graph and two nodes S and T, such that any algorithm requires at least 1 over epsilon queries to epsilon approximates the ST effective resistance. The high-level idea behind the algorithm is the pyroresistance formula. So we consider the graph. We consider the resistance from the top line as R1. We consider the resistance from the bottom line as R2. Then the pyroresistance formula tells us that the ST effective resistance, 1 over the ST effective resistance is given by 1 over R1 plus 1 over R2. So our construction is based on this observation. We consider an expander graph on S1 with N1 vertices, and we consider S2 is just N2 isolated vertices, and the size of S2 is much smaller than S1. Then we connect T to all vertices in S1 and S2, and we connect S to D neighbors, where in G1, all neighbors are connected to S1. In G2, 1 minus epsilon fraction of the neighbors are connected to S1, and epsilon fraction of the neighbors are connected to S2. And the observation is that when we only consider the resistance from the upper part, RS1 is actually 1 over 1 minus epsilon times D plus a little O term. And if we only consider the resistance from the bottom line, then RS2 is actually 2 over epsilon D. And then by the pyroresistance formula, we have that the second graph, RG2, is actually 1 over D times 1 plus omega epsilon. However, the first graph is 1 over D, 1 plus little o epsilon. And this is the difference. So RG1 and RG2 differs by at least epsilon in terms of the relative error. However, to distinguish G1 and G2 requires at least 1 over epsilon queries. So therefore, 1 over epsilon queries are necessary for the local effective resistance approximation on the expander graphs. And I think this makes sense. And I think I have no time for the presentation of our third result. So I skip this part. Finally, the conclusions and the future directions. So in this paper, we studied the algorithms and lower bounds for the local effective resistance computation. For the future directions, the first one is tighten the upper bounds and lower bounds on the expander graphs. The second one is the improved condition number dependency for the local effective resistance computation on non-expander graphs. This is because all the proposed algorithms in this paper relies on the condition number. And also the lower bounds on the condition number is also under studied. For the third problem is to improve the effective resistance computation on general graphs and also study the tighter lower bounds. Thank you.
Questions for the speaker?
Hi, thanks for the talk. So at some point, I saw that your algorithm has the square root dependency, and the lower bound doesn't have any dependency on D at all. And can you comment a bit on like where maybe this dependency is coming from? And I guess I have guessed that this comes because you're using coordinate gradient descent.
This is because the deterministic part will at the cost of larger dependency on the graph structure, and but combining the deterministic algorithm and random walks, we can reduce the variance. So we can expect that the epsilon dependency is lower, but there's a higher dependency on the degree of the graph.
And so just a quick related question. So in the deterministic part, instead of using like coordinate gradient descent,
Yes,
did you
yes.
think about using something else to adapt better to like the structure of the problem, or you haven't looked at that to use like something different than gradient descent, something else? Like
Yes,
mirror descent?
maybe this is a variant of the coordinate gradient descent.
Okay. Yeah, sounds good. Thank you.
Thank you.
Any other questions? All right, let's thank the speaker again. Okay, and our second talk of the day will be about metric embeddings, and the talk will be given by Amit, who's not one of the authors, but is thankfully filling in for them.
Hi, everyone. Thanks for coming. Today I'll be talking about this paper on metric embeddings beyond bi-Lipschitz distortion by these authors, Ainesh Bakshi, Vincent Cohen-Haddad, Samuel Hopkins, Raj Jairam, and Silvio Latanzi. So I guess in all metric embeddings problems, the setting is you have some high-dimensional data, maybe a bunch of points in Rn, and you want to embed these points in some low-dimensional space, say Rk. And for some notion of approximation, you want to approximately preserve the pairwise distances between these points. Slightly more concretely, say I have some metric over n points. So I have this metric described by the distances dij for pairs I and j and n. And I want to embed these points into Rk. And here, think of k as being some small constant, like 4 or something. And I want to embed these points in Rk as points x1 through xn, such that for every pair I and j, the distance is preserved in this sense. So the ratio between the distance between xi and xj and the true distance, dij, is bounded by some number L. This is the canonical goal, which is usually considered. And this is often referred to as the bi-Lipschitz, or worst-case distortion. So what do we know about results for this? I guess there's a hardness result, which shows that it's NP hard to approximate the optimal number L by a multiplicative factor better than n to the order 1 over k. And this n to the order 1 over k approximation is attained by the Johnson-Lindenstrass algorithm, where you just project these points in Rn down to a random k-dimensional subspace. Right? So this very simple algorithm attains n to the order 1 over k. So it seems like the picture here is not super interesting. Right? So there's not really any interesting algorithms here, and maybe the optimist would say that this notion of bi-Lipschitz distortion is a poor yardstick for comparing efficient metric embedding algorithms, because there's this very simple algorithm that does the best you could hope for. Towards that, we're going to consider this different objective called the Kamada-Kawai objective. And over here, this enforces some asymmetric penalty on the embedding. Right? So, okay, let's look at this distance. First off, it's not a worst case thing over all pairs. I have some expectation over pairs I and j. And furthermore, I'm not just going to look at the ratio of the distances. I'm going to look at something slightly different. And essentially what this something different is doing is that contracting distances, so if I and j are close by, then contracting the distance does not hurt you too much. So it only contributes a 1 to the expectation in the worst case. Whereas if I expand a distance, so xi minus xj is much larger than dij, then it could contribute a lot to the expectation, which is pretty bad. So what is this doing? Roughly, what it's doing is that it keeps nearby points close by. So if there's some cluster structure in my original points in the metric, then it preserves this cluster structure in the embedding. And as a baseline for what you can hope for, if you embed all the points to, if you set all the xi to be the same as 0, then you get that the expectation is 1. So at the very least, opt is at most 1. So it's a number between 0 and 1. OK, let's look at what algorithms we have for this. First, you could try doing the same Johnson-Lindenstrass thing. So it turns out that there's some combination of a very simple SDP plus the same random projection Johnson-Lindenstrass step, which finds an embedding whose cost is opt plus order 1 over k. But this is not too great, because you should be thinking of k as being like 4. So this is actually additively a constant worse than the best you could hope for. On the other hand, another algorithm you could try is just principal component analysis on this strange matrix, identity minus 1 over n, 1, 1 transpose, and then the matrix of squared distances multiplied by identity minus 1 over n, 1, 1 transpose again. And while this works OK in practice, there's no real provable guarantees for this. So as a concrete example, suppose I have this two-dimensional example on the left, where I have a bunch of points, and there's like clusters of triples of a bunch of these points. And within each cluster, the x coordinates are all the same, but the y coordinates are slightly perturbed. Then if I try the PCA approach, I just pick the direction of maximum variance, and I project onto that direction. So actually, every triple just collapses down to a single point. But it turns out that the optimal Kamada-Kawai projection, it actually preserves some cluster structure without trivializing the clusters. So these distances are well separated in the actual optimal projection. There's another approach in this paper by Domain, Hesterberg, Kohler, Lynch, and Urschel, where they reformulate the Kamada-Kawai optimization problem as a dense CSP. And in the running time of the CSP, an important thing that enters the picture is the aspect ratio of the metric, which is the ratio of the maximum distance to the minimum distance between 2 points. And what they show is that for the aspect ratio delta, in time n square multiplied by 2 to the poly delta over epsilon time, you can get an opt plus epsilon approximate embedding. Right? So as I said, what this algorithm does is that it reformulates the Kamada-Kawai optimization problem to a CSP instance where you lose an epsilon. And once you get the CSP, you just solve, you just approximate the optimum of the CSP using some black box dense CSP solver. What the authors show is that you can get objective value opt to the order 1 plus epsilon time. But the upshot is that the running time of this algorithm, instead of being 2 to the poly delta over epsilon, it's 2 to the poly log delta over epsilon. So as a concrete example of why this running time could be much better, maybe think of the setting where the metric you have actually comes from something that is a true low-dimensional metric. So I have a bunch of points in R4. In this case, the aspect ratio delta is actually going to be omega n if I have n points. But maybe I perturb these points by a little 1 over poly n amount. And that essentially means that opt is not 0 anymore, but it's like 1 over poly n. Then if I did the dense CSP algorithm from the previous slide, then because delta is order n, the running time of the previous algorithm is actually going to be 2 to the poly n over epsilon, so like exponential time. Whereas the author's algorithm, which is based on this Sherali-Adams hierarchy, it runs in time just 2 to the poly log n, right? So it's much better running time. And the main technical innovation in the author's work is that they still go through the same dense CSP approach, but when solving the CSP, instead of just applying some black box solver, they set up the approximation algorithm in the Sherali-Adams hierarchy, which is the series of convex programs. And they do the usual thing of global correlation rounding, which is present in these algorithms. But in the analysis of global correlation rounding, they're really able to leverage the fact that this is not an arbitrary KCSP, but it instead comes from some low-dimensional metric structure. And they're able to leverage this low-dimensional metric structure to beat the naive running time of 2 to the poly delta over epsilon and get this win of poly log delta over epsilon. Okay. To conclude, let me give a few open problems. So it turns out that you can't hope for an FP task for Kamada-Kawai unless P equals NP. So what this says is that you can't get like a 1 plus epsilon multiplied by opt approximation. But you could ask whether, okay, you can get an opt plus epsilon approximation similar to the earlier paper, or an order opt approximation in time that does better than the 2 to the poly delta over epsilon. So I guess over here, like maybe poly delta is the dream, right? And another class of questions is whether you can just consider different metric embedding objectives other than the Kamada-Kawai objective. And as examples, maybe consider this thing where I have the same expectation, but I weight the pair ij by some number wij. So if all the wij are 1, then I just get Kamada-Kawai. If I said wij is dij, I get this other thing called salmon mapping. wij equals dij squared gives this other thing called raw stress. And these are all extremely well-studied metric embedding objectives. There have been like whole books written on this class of metric embeddings called multidimensional scalings. And okay, another example is this thing called the Kruskal stress, where I have something that now looks pretty different from the Kamada-Kawai objective. And yeah, okay, do the ideas in this paper provide any insight to approximation algorithms for these other objectives? Okay, yeah, that's it. Correct. So, okay, my understanding of the proof is that the way the usual dense KCSP approximation algorithms go is that you set up some CSP, and over here it's going to be a CSP over alphabet size, like poly delta, okay? And when you have this alphabet size of poly delta, usual algorithms based on this same global correlation rounding thing, they have to, they need like 2 to the poly delta many rounds of the Sherali-Adams hierarchy. So that's the degree of the setup. But over here, because the instance is coming from some lower dimensional metric, you can actually beat this significantly. And just in the analysis, they can show that it suffices to consider far fewer levels of the hierarchy, and you can get this polylog delta. Yeah.
Do you know if they got the slides? They got the slides. Okay. Yeah. Okay, great. So our third speaker will be Xin Li, talk about tight bounds for noisy computation of high influence functions, connectivity, and threshold.
Yeah, okay, thank you. So this is joint work with Indro Gu and Injan Shi. So unfortunately, they cannot be here, so I'll be the one to present this work. Okay, so how do I control the slides? This one? Okay, oh, great. Okay, great. So let's start with the model of the noisy query model here. So basically, the task here is, again, so we're given the Boolean function. And then we want basically to compute this function. And so there's, the input here is an unknown vector. So think about it as n-bit strings. So this is not given to you, but of course you want to compute the output of this function. And then the way to do that is you can use query access to this input x. But the catch is that each time you query this bit, the answer is not exactly the bit, but the bit will be flipped with some constant probability, let's say p. So think about it, let's say 1/3 or something. Doesn't really matter. So this corresponds to a noisy query model. So one typical situation could be, so you're the one who's on the phone with somebody else, and then the other one is listening to the music, and then each time he gives you the answer is going to be noisy. And then, of course, here we allow the queries to be even randomized, and we can also use repeated queries. And the goal, of course, is to compute this output of this function, and then, of course, we would have to allow some small error probability here. And the goal in this query model is basically to try to minimize the number of queries. So this is the basic query, noisy query model here. This model actually has a long history here. So it was actually first formally defined in this paper by Feiger and his co-authors. So they first formally proposed this noisy query model. And then they actually studied several problems in this model and decided this noisy query model. There are noisy query complexities, including parity threshold functions, binary search, and sorting. And in particular, this noisy binary search problem was actually studied even before this work, studied first by Breckham in 1964, and then there are a bunch of following up works. But actually, if you look at these results, then most of these results actually concerning specific functions. So there are only a few of these results which actually works for general functions. In particular, we have some lower bounds like omega n times log n for random functions. And we also have a general upper bound of O n times log k for k seeing f and k dealing f's. And in fact, many learning problems can also be viewed as noisy query problems. So some examples here include active top k selections. So these are learning from noisy comparisons and also noisy group testing. Okay, so again, so the question here is to decide what is the noisy query complexity of a general function. So there are some pretty easy to get trivial upper bounds. So for example, by definition, the noisy query complexity of a function is at least the randomized query complexity. And you can also get an upper bound because you can simply, for example, repeat each randomized query by this number of times and take a majority. So this gives you a trivial upper bound of order Rf times log Rf. And because we know, of course, the randomized query complexity is always at most n, so order n times log n is actually a trivial upper bound. But if you look at specific functions, then they sometimes, even if their randomized query complexity is the same, so their noisy query complexities are actually different. So for example, for the OR function, the randomized query complexity and noisy randomized noisy query complexity are both theta n, whereas for parity, the randomized query complexity is n, but the noisy query complexity is actually theta n times log n. So the question we study here is it possible to actually determine the noisy query complexity for a general class of functions rather than specific functions? So here is our result. So our main result, the first main result is we show that if a function has a very large total influence, say if the total influence is omega n, then the noisy query complexity is actually omega n times log n. So this basically matches the trivial order of n times log n upper bound. And this also unifies the previous results on parity functions and random functions, because these functions actually have very large total influence. Prior to our work, the only known general bounds was just for random functions. Okay, so our second contribution is to actually decide the noisy query complexity of this very basic graph problem, the graph connectivity problem. Okay, so I think everyone here knows the graph connectivity problem. Basically, you're given an undirected graph. You're trying to decide if the graph is connected or not. So for example, the graph on the right is connected, and the graph on the left is not connected. So it's a very basic problem, but surprisingly, prior to our work, we don't actually have a very good bound in terms of noisy query complexity of this problem. So our second contribution basically is to prove that solving graph connectivity actually requires omega n squared times log n noisy queries. And again, so this matches this naive order of n squared times log n bounds. So again, notice here the input, of course, has sort of n squared entries because we're counting the edges of the graph. And you can also, and this also implies bounds for other graph problems, which I'm not going to talk about here. So we also have results for some other problems. One of them is this so-called case threshold problem. So the problem is to decide, you are given MB strings, and you decide how many ones are in this string. So in the work by Feiger et al., so they proved an asymptotical optimal bound of theta n times log k over delta. And then there are recent works which tries to sort of optimize the constant within this theta. Basically, the final result is something like almost close to 1 times n times log k over delta divided by the k-out divergence between these two Bernoulli distributions with head property p and 1 minus p. Except the previous problems only work for special cases, like the case where k equals to 1, or maybe k is small on. And here we basically get the result for them, or essentially all the cases. So we get this pretty tight bound. And of course, so another related problem is counting. So we're trying to count the number of ones in the n bits. And we also get a pretty tight bound of something like this. Again, so we have something roughly is n times the logarithm of the sort of like L1 norm divided by the k-out divergence. Okay, so I'm just going to give a very high-level proof idea here. So our proof is based on the previous work by Feiger et al., and then we're going to extend their framework. So they gave us sort of like a two-phase analysis. So here we extend it to three-phase analysis. See, the first step, so the algorithm is going to make some non-adaptive noisy queries to each one of these bits. And then the second step is basically the most important step in our proof. So this is a new step we add to our work. So we're going to carefully design some free information that is going to be disclosed to the algorithm. And the advantage of doing this is by controlling this free information, we can actually carefully control the posterior distribution of the input, given the queries and also the free informations. So this is going to make the analysis easier. And the last step, we're going to do something similar to the previous work by Feiger et al. So we're going to allow the query algorithm to make adaptive queries, but here we're going to make exact queries instead of noisy queries. So that's a rough idea of the proof that goes into our work. So in order to carry out the proof, it turns out that one tricky part we need to do is to design a suitable distribution on the inputs. And for the high influence functions, we actually just use the simple uniform distribution over the inputs. Whereas for graph connectivity, we use a distribution based on the uniform random spanning trees of the complete graph. For case threshold and counting, we actually give a direct reduction from one of the previous works. And we can simply generalize the algorithms and the bounds to essentially all the cases. Okay, so here are some open questions. So the first one, which I think is the most interesting question, is we have this open question whether the noisy query complexity of a function can be lower bounded by something like the total influence times log of the total influence. And we essentially solve the case where total influence is sort of omega n, so sort of like the largest case. And it'll be very interesting to see if this conjecture actually holds for all the possible total influence. And another minor interesting work, I think, is to decide the exact first order constant of the noisy query complexity for the case selection problem. So we only did it for like case threshold and case counting. For case selection, the constant is still not decided. So that's one of the open questions. And I think that's all. Thank you.
Okay, thanks. Any questions for the speaker?
So can you think similar approaches can be applied to group testing as well?
Oh, that's a good question. We haven't actually checked that, but yeah, I think maybe something can be done there. So yeah, it's a good question.
Yeah, I have a question. So for the result on graphs, do you know? So it sounds like you were directly using the spanning tree. So I guess your graph instance is a complete graph.
Right. So we're actually using distributions on these spanning trees. Yes.
And does that approach prove anything about the influence?
No, it doesn't directly follow from the influence because here, in the case for general graphs, the influence can actually be small. So we have to adjust the distribution. So we're using a special distribution here.
I see. So and under that special distribution, it doesn't say anything about the influence?
Not directly, but it could say something. So we need to check that. Yes.
Okay. Interesting. Interesting. Are there, as for your open questions, I guess for the, what is the influence of the OR function?
For the OR function, actually, is also pretty small.
It's
so
like constant,
yeah,
or
something like that.
Okay. So are there other interesting examples where this open question would give like tight results that we don't know?
Yeah, that's another good question, I think. So one thing is, of course, you can get some, if this is true, then you can get some lower bounds, but then if it's tight, if you want to say it's tight, then you have to also prove upper bounds. Yeah.
Mm-hmm, mm-hmm. Right, yeah. Okay. Any other questions? Okay, let's thank Jin again.
Yeah, it's working. Hello everyone, my name is Hao Dongzhu. Today I will present our recent work, Noisy Group Testing in a Linear Regime. This is a joint work with Lucas Kins, Lina Craig, and Olga Shevtovich. I think what group testing has already occurred in the previous talk, and I will explain this in details. So the group testing was originally introduced during the Second World War when people want to efficiently detect a certain real disease among soldiers. in recent years, because it has also gained a lot of attention, especially during the COVID pandemics. Apart from disease detection, it is also used in detecting carriers of genetic disorders and finding hidden subgraphs in a network. In group testing, we can see the population of n individuals, where each individual is infected with a property alpha. This property is a constant in our setting. In this graph, we illustrate all individuals by cycle, and the plus beam means that this individual is infected, and the minus beam means this individual is healthy. In total, we can perform M tests, which are present by squares in this graph. Each test can contain an arbitrary number of individuals, and this containment relationship is represented by the lines connecting cycles and the squares in this graph. Ideally, a test is positive if at least one individual participating is infected, and negative elsewhere. However, in reality, test outcomes might be affected by noise. As a consequence, the observed result might be different from the ideal results. And we model this noise in the real world by a binary noise channel. In this noise channel, for each ideally positive test with probability P10 it will flips, and with probability P11 it will stay positive. Likewise, for each ideally negative test, it will flip with probability P01 and stay negative with probability P00. We assume that P01 plus P10 is less than 1, such that the noise does not dominate the channel, and we assume that all test flips are independent. The goal of our group testing is to exactly recover the true status of all individuals while using with high probability, while using using the smallest number of tests. Oh, sorry. In reality, there are two types of tests people are mainly interested in. The first one is non-adaptive group testing, where all the tests are designed beforehand and can be conducted in a single round. The second one is the adaptive group testing, where all tests can be designed based on previous results. In this way, we can save the number of tests, but it might need several rounds for us to conduct the test. In reality, we want the number of rounds to remain a constant as n grows. In this project, we mainly have two main results. The first one is the information theoretical lower bound Cn log n for both adaptive group testing and non-adaptive group testing, and we pin down the constant C in front of Cn log n. Furthermore, we can design algorithm to achieve this information theoretical lower bound with a running time of the order of n log n. But let us first ignore all the test design and consider the following decoding problem. If you are given all the tests and their observed results, what is your best guess of the sigma, which is the true status of all individuals? The answer is the following map estimator, whose value equals to the number maximize the conditional probability on the right-hand side. So the thing seems to be easy. We can just design tests, get a test result, plug them in a map estimator, and get a prediction. However, this map estimator is very hard to analyze because this is a global estimator. To overcome this problem, we aim to find some local estimator which makes the computation to be easier. So, yes. If there's a genie who finally tells you the infection status of all individuals except the individual I, what is the best guess you can make for individual I? The answer is again Similar to the previous map estimator, it is the Falling Gini-based estimator whose value equals to the number maximize the conditional probability on the right-hand side. And we see that in the condition, there is a sigma minus I, which corresponds to the information you obtained from the Gini. There are two advantages of this Gini-based estimator. The first one is it is a kind of a local estimator in the sense that if we change the test results of a test which does not contain I, the Gini prediction of individual I will not change. The other thing is that this Gini-based estimator is better than a map estimator in the sense that if the Gini-based estimator cannot achieve exact recovery, the map estimator cannot as well. It can also be shown that the accuracy of the Gini-based estimator for individual I depends only on the good tests, which are tests includes I and do not contain any other infected individuals. In fact, if there is infected individuals contained in this test, then no matter this individual I is healthy or not, the ideal test results will always be positive, and this test result will give you no information of the infected status of individual I. It can, by large deviation theory, we can also show that the property that Gini-based estimator make a wrong prediction on individual I declines exponentially as Ji, the number of good tests of I increase. Hence, if we want to achieve exact recovery with high probability, each individual needs to receive enough good tests. In a non-adaptive case, the number of good tests one individual receives fluctuates. And by using the Gini-based estimator, we can show that it has an information theoretical lower bound of the form Cn log n, while the constant C is of the following form. It is worthwhile to mention that the gamma on the right-hand side, which minimizes the function here, is equal to the optimal number of individuals a test contains. In an adaptive setting, since a test can be designed according to previous results, like it is possible that likely infected individuals receive more individual tests, and likely healthy people receive more group tests. In such a way, we may reduce the number of tests we needed. So we can also obtain an information theoretical lower bound for the adaptive group testing, also of the form Cn log n, but this C is smaller than the C we obtained in a non-adaptive group testing. Here is the graph of the. Here is two graphs illustrates how the value of C increases as the number of alpha. The probability that individual get infected increase. It is worthwhile to mention that in a non-adaptive case, for large alpha, the C stays the same. It corresponds to a case that the gamma minimized the function on the right-hand side is equal to 1. And in this case, most of the tests designed in the non-adaptive group testing should be individual tests. On the contrary, in adaptive group testing, in all the case, most of the tests being included in a test design should be individual tests. I think I do not have time to talking about the algorithm, so maybe I can start with the open problem. So the noisy group testing in our setting has been well studied, but there are many open problems in other fields, and we mentioned two of them. The first one is the noisy group testing in a sublinear regime, where the number of infected individuals grows sublinearly in N. This setting is only well stood in some special case like constant current design, and it will be very interesting if one can obtain a general theory for this case. The other is the partial recovery. In practice, exact recovery may not be necessary, and it will be very interesting if one can determine the minimum number of tests one requires to achieve some partial recovery while some areas are tolerant. Thank you for your listening.
Great, thank you very much. Any questions? Okay, I have a question.
Yeah.
So, I'm not an expert on group testing, but I remember seeing slightly different versions of the problem before. So,
Yes.
I guess one common setting that you might see is like if there's only one a sick person that you want to identify,
Yeah.
or I guess you could say more generally, maybe you assume a bounded number of sick people.
Yeah.
Would your work give any results for that setting?
No, because during a corona pandemic, group testing also gains a lot of attentions, and in these settings, there are a positive proportion of people have already get affected,
Right.
and we are more interested in this case. And I think our settings, it's not easy to apply our settings to a case when the number of infected individuals is limited.
Right, I see.
Yeah.
So I guess you're kind of sort of imagining that like you're in the kind of high entropy case where you
Yeah.
have like roughly half the individuals are
Ye-
infected.
yes,
Yeah. And aiming for like precise constants
Yeah.
like C
Yeah.
in that case. Okay. So even if you knew it was like like an alpha n fraction,
Yeah.
could conceivably you get your constant C to depend on alpha?
Yes, the constant C is depend on alpha, which you can see from this graph. So actually, in adaptive case, the constant C grows linearly with alpha.
Here alpha is the noise
No,
threshold.
alpha is the proportion of individuals get infected,
Oh,
and
alpha is the proportion. Oh, okay.
yeah, and the
okay.
P11 and the P01 are comes from the noise channel.
Okay,
Yeah.
got it. Okay, thanks. I misunderstood. Yeah. Okay. Okay. So in the first equation, is it clear? I guess I'd have to think what the dependence is on alpha there. Is there like a more? Is it easier to see how that depends on alpha?
So basically, we have a gamma there.
Yeah.
Yeah. So when alpha increase, we are more likely to obtain individual tests in this setting, and there's a horizontal line in a graph, which will correspond to a case that alpha is so large such that almost all the tests are individual tests, even in a non-adaptive case.
Okay. Got it. Okay.
Yeah.
Thanks very much. Okay, let's thank the speaker again. Yes. Okay, great. You ready to go? Yep. Okay. All right. Great. So our next speaker will be Sachin Garg, who will talk about low-rank approximation.
Hello everyone, I am Sachin and I will be presenting this work on block Nystrom method done jointly with my advisor Michal. And how does this work? I see. Okay, so let's begin with the problem formulation. The task at hand is providing a low rank approximation to a PSD matrix A, and we want to achieve this efficiently. Now, such a low approximation task has various applications. A few of them I have mentioned on the slide, but there are numerous others, okay? And the first ambiguity that we should resolve here is, what do we mean by approximation, and how do we define it? So let's fix that first. Suppose alpha is your desired approximation factor, and there is some positive lambda. We say that A hat is a lambda regularized alpha approximation to A if the following condition holds. Now, alpha here is controlling the approximation quality. That means if I take alpha to be O of 1, then I'm constructing a very fine approximation to A. And if alpha is n raised to some exponent theta, maybe theta is very small, we are considering a very coarse approximation to A. And here's a brief outline of the talk. First, I will do a very quick background review of this Nystrom method. What are the guarantees it provides? How do we construct it? And what is one challenge that we are facing? Then I will going to propose our work, block Nystrom method. How do we construct it, and how do we resolve the challenge that we are facing with this classical Nystrom approximation? And if time allows, I'm going to cover one of the application of the block Nystrom to see what can it achieve in specific problem settings. So let's begin. Okay, so Nystrom approximation is a very classical technique for constructing low-rank approximation to PSD matrices. And here is how it goes. So you start by selecting m indices from this set 1 to n, often known as selecting m landmarks. And once we have selected these m landmarks, we go and sample the same columns from from A and put them in this matrix C. We also sample the principal submatrix W, which is also indexed by the landmarks that we have sampled. And then the Nystrom approximation A hat is given by C times W inverse C transpose, because W need not be invertible. That's why there's a pseudo inverse sign over there. So that's the factorization for the Nystrom approximation. And because we have sampled m landmarks, this is known as a rank m Nystrom approximation to A. And we can visualize this as well. Suppose this square is representing A. These are the landmarks that we have sampled. And the Nystrom approximation can be visualized with this factorization. An immediate question that comes here is, how are we actually sampling the landmarks? And in fact, the simplest thing that you can do is sample the landmarks uniformly. And you can, in fact, prove some guarantees with the uniform sampling as well. Also, you can design some very increasingly sophisticated importance sampling measures to do that. But in recent time, literature seems to be converging on sampling the sampling landmarks using these lambda-rich leverage scores. So what are they? So the ith lambda-rich leverage scores of A is given by diagonal entry of this matrix A times inverse of A plus lambda I. And another quantity of interest is, what do these leverage scores sum up to? The sum of these leverage scores is known as lambda effective dimension of A. But it turns out we cannot find these scores exactly, because doing that would be as expensive as doing the eigen decomposition of the whole matrix. But fortunately, we can approximate these scores up to a constant factor in time n times square of the effective dimension. Okay? And these are the guarantees when we combine the Nystrom approximation with these importance sampling. The A and A hat are in spectral norm error, they are apart by at most lambda. The second property says that we can apply A hat and its inverse to any vector x in almost linear time. And the third property is what we are aiming to achieve, this alpha approximation. It turns out Nystrom approximation achieves this with O of 1. Okay, so what's the problem here? What are we trying to resolve? And the problem is that you can see highlighted in red, we have to approximate these scores. And these scores cost has a quadratic dependence on the effective dimension. And it turns out when the matrix A has heavy tail spectrum, or in simple words, the eigenvalues are not decaying fast enough, this effective dimension could be really large. In fact, it can be as large as square root of n, or lie arbitrarily from square root of n to n. So in those cases, this term itself becomes a dominating cost, and we cannot proceed with the method. So what's the way out? One way out is, rather than asking for a very fine approximation, ask for a coarse approximation. That means instead of approximating lambda-rich leverage scores, construct this lambda prime scores for lambda prime, which is much larger than lambda. And then using those scores, construct a coarse approximation for alpha, which is some exponent in n, okay? And theorize something that we get to choose. So keep this idea in mind that we are moving from fine approximation to coarse approximations. And that's where we propose our work, which is block-Nystrom method, to achieve these coarse approximations. So we propose this data structure, block-Nystrom, that provides this alpha approximation guarantee. But as you can see that I've highlighted in this color, we are using alpha squared times lambda rich leverage scores. And one thing to keep in mind is larger the lambda, smaller the cost to approximating those scores is. Well, how does it compare with the classical Nystrom? In comparison, the same guarantee with Nystrom would require alpha times lambda rich leverage scores of A. So you can see there is a difference by a factor of alpha. But what does it mean? How does it translate to actual cost of the algorithm? Here's one concrete example. Suppose if A has polynomially decaying spectrum of certain degree gamma, gamma is between 0 and 1, then we are getting computational gains of the order of n raised to 2 to the theta gamma. So in heavy tail spectrum settings, these gains can be quite remarkable. And this is the main theorem, the informal version of the theorem that we prove. We propose this data structure A hat, aka block-Nystrom, with certain rank, m, can be constructed in certain time complexity. You don't have to worry too much about this time complexity. The only point is it's much better than the classical Nystrom one. And we prove these three guarantees. First one is we are achieving an alpha approximation. Second property is this data structure can be applied to any vector in linear time. And the third property is we can implicitly invert this block-Nystrom structure rather than, it has some complicated structure, but still we can implicitly invert it in almost linear time. Not exactly linear, but almost linear. And let's have one slide on how are we actually constructing it. The first step is obvious. We need to approximate alpha squared lambda rich leverage scores of A. And the second step is we are going to sample multiple smaller Nystrom blocks. We are going to sample these Q Nystrom blocks. That's A1 hat, the first one. Then we have the second small Nystrom block. Then we have the QS1. And we combine all of them to recover this block-Nystrom data structure. So that's how you can visualize the data structure that we are proposing. All that is fine, but what's the main idea behind doing all that? Why are we able to achieve these gains? So on this slide, I'm trying to just give a very high-level idea of why is this true. If you look at the first math expression, that's saying that in terms of spectral norm error, the expected Nystrom and the Nystrom, both are kind of the same. So expected Nystrom is not doing any good job over there. But when it comes to spectral approximation, somehow expected Nystrom is better than Nystrom by a factor of alpha. Okay. And another way to see this is by this figure. Okay, you can read the line over there, but I'm going to present this by this figure. On the y-axis, we have eigenvalues. And on the x-axis, we have index of these eigenvalues. The plot has two parts. The left part is bias region, and the right side is variance region. And there are three plots over there. The blue part is A, the green line is the Nystrom, and the orange line is expected Nystrom. So if you just focus on that highlighted part, you can see as soon as we start to transition from the bias region to the variance region, how quickly the Nystrom goes. It's basically 0 after that point. And whereas expected Nystrom keeps following the trend and keeps approximating it at least to some distance. Okay? And this is what is very phenomenal. So this actually gets related to this bias variance trade-off that we keep seeing in many machine learning applications. In the bias region, A and A hat, Nystrom and A, and expected Nystrom, the lines are coinciding. But when you move to the variance region, the story is different. As soon as in the starting, the story is different. And let's zoom into that picture more. Now we have regularized all the three methods by this amount, lambda, and see what happens over there. The blue line and the orange line are quite close to each other. But the good point is, this orange one, which is the expected Nystrom, regularized expected Nystrom, it's much better than the regularized Nystrom. And this is the main observation that we exploit in our construction of block Nystrom. We cannot use the expected Nystrom, but we kind of combine multiple small Nystroms to propose this data structure. And we exploit this phenomenon by using matrix concentration inequalities. Now I'm going to briefly talk about this application. There are multiple applications in our paper, and one of them is quite subtle to talk about in this talk. So I'm going to present a simpler one, which you can more easily comprehend. So this is a theorem. We propose a block Nystrom preconditioner, which can be used to optimize any strongly convex loss, which has this form. Rather than going over the details of this theorem, let's see a representative example. So suppose A is some matrix, which has at most k large eigenvalues. What I mean by that is, after the kth eigenvalue, all the remaining words are within a constant factor approximation of the smallest one. Okay. And this model is not completely made up. It arises in various spiked covariance models and other settings. So it's kind of an important one. And suppose the task at hand is this quadratic minimization. So there is this function g, which is quadratic in x, and the Hessian of the function is a. Okay. This is a theorem that we prove. Suppose a has at most n raised to 0.82 eigenvalues larger than its smallest eigenvalue. Okay. So in this figure, this flattening part happens at around n raised to 0.82. Then we can provide an epsilon approximate solution to the quadratic problem in time n raised to 2.044. And how does it compare to the previously existing state of the art? Well, the previously existing work was doing this in n raised to 2.065. So although the improvement is kind of marginal, but still there is some improvement. And there are other line of works which follow completely different strategy. They achieve the runtime of n squared, but they only do for k raised to k being n raised to 0.76. But we are extending that work to kind of 0.82. So in that scope, our results are kind of wide in scope of coverage. And these are a few concluding remarks. The first one we have seen in this talk. There are at least two more ideas in the paper. The first one is, which I did not talk about at all, is how are we implicitly inverting this bit data structure? So we use this approach based on recursive preconditioning. It's a novel approach. So I encourage you to go and have a look at that. Another more subtle application is we do near optimal kernel ridge regression over Hilbert spaces. And we cover these hard learning scenarios, which essentially translate to when the regression function in the reproducing kernel Hilbert space, it cannot be well approximated by the linear functions. So that's another application where we obtain this computational gain. And I think that's my time. Thanks for your attention.
All right, any questions? Okay, I have a question. So thanks for the very interesting talk. I was trying to follow all the details. There's quite a lot. So in the last application, like how would this compare to standard methods, like gradient methods, etc.?
Yeah. So for solving linear systems, the go-to approach is preconditioned conjugate gradient. Mm-hmm. So those algorithms have a condition number dependence. So it would be like, so every step, every iteration is like n squared, and then you have a square root of the condition number. Mm-hmm. So first, these approaches are, our approach is there's no condition number.
Mm-hmm. But you do have these eigenvalue assumptions, which in some sense are like similar to a condition number assumption.
Yes, so that's what, we use this block Nystrom as a preconditioner to get rid of the condition number of the problem. Mm-hmm. So the cost is actually constructing the preconditioner so that the condition number goes away from the problem. Yes. I don't know if that answers your question, but that's why you do not have that square root of kappa or any condition number dependence in the final result.
Interesting. Yeah, maybe I can get more details from you offline about that.
Sure.
Uh-huh. Okay. Yeah. Okay. Any further questions? Okay. All right. Let's thank the speaker again. They didn't tell me any issues, so I'm assume it's okay. Yeah. Okay. Perfect. And the clicker. Oh, where did it go? Ah, here we are. Yeah, this one. Okay. And what's your name? Yeah. Okay. All right. Great. And this is our last speaker of the session. So the speaker will be Panos, optimal scheduling of dynamic transport.
Hello. Hi. All right. All right. Hi, everyone. I'm Panos, and today I want to present to you joint work with Ziren Jacob Zeg and Youssef Marzouk. And the title of our work is Optimal Scheduling of Dynamic Transport. So let me jump straight into it. Okay, so for context, let mu and nu be measures, probability measures, and we want IID samples from nu, but we can only generate IID samples from nu. How do we solve this problem? Well, one way you can do this is you can find a transport map T, which is just the map from RD to RD, such that if you apply the map on the samples from nu, you get samples from nu now, statistically. And that's equivalent to saying that T pushes forward mu to nu. This is the standard setup of sampling with transport maps. Okay. One way to do this is to do what's called dynamic transport. And what we do here is that we look for a velocity v, we solve an ODE, like the one I'm showing you here, and then we say that, okay, the transport now will be the time one flow map of the ODE, right? And the way to visualize this is you just think of mu as like a Gaussian or something. You draw a bunch of samples. These are like particles in space. And then you run your dynamics. So this V is a velocity field. It specifies some dynamics. Your particles follow streamlines for unit time. And then you end up with particles from your target distribution. All right. For example, let's take mu and nu to be standard Gaussians. In one dimension, zero mean, and some variance. And let's also, in this example, I didn't write this down, but let's assume that theta 2 is much larger than theta 1. Let's take T to be a linear map. And this will, in fact, push mu forward to nu. This is the Monge map, for those of you who know. This is the optimal transport map. And let me specify the dynamics, the flow map, to be this affine interpolation between the identity and T. So what this means is that every particle now travels from x to T of x on a straight line. And tau there is a new degree of freedom, which is a map from 0, 1 to 0, 1 that fixes the boundaries. This specifies the rate at which your particle travels from x to T of x, right? And this would look sort of something like this. On the y-axis, I'm putting the time variable, and on the x-axis, I'm putting the position of the particle. So at time 0, the particle starts somewhere, and then it kind of travels following the dynamics. And what I want you to notice is that these are plots for two different taus, and they look quite different. On the left, I'm showing you tau equal to the identity, so tau of t equal to t. The particles travel with constant rate on the ray connecting x to T of x, whereas on the right, I'm speeding up the particles at the beginning, and I'm slowing them down at the end. And the way to think of this is to look at the particle that starts at time 0 at position -4, so this is the bottom left corner. If you look at where this particle has gone at time 0.5, then on the left, it has traveled a lot less towards its final destination than compared to on the right. And because I'm doing this to map this larger Gaussian to this tighter Gaussian, all of the particles are moving towards the origin, right? On the right, faster at the beginning, slower at the end. On the left, constant rate. Okay. Why do we care about having these pictures look different? Well, on the left, the spatial derivative of the velocity field at time 1 is much, much larger than on the right, right? So the velocity field here will be tangent to those rays. And you can see that at time 1, there is this corner that is forming, right? Because all of the particles are traveling at a constant direction, constant rate, and now they're very, very close to each other. So neighboring particles that had same direction and same rate will be very close. So if the derivative is change of velocity over, unit of space, this naturally is going to blow up. But on the right, I'm slowing down the particles as I'm approaching the singularity. So generally, this quantity, this derivative at time 1 is going to go down. Visually, you have a corner that is forming on the left, whereas it's much, much smoother on the right. Another way of saying this is that the Lipschitz constant at time 1 is going to be much larger on the left than on the right. And why do we care? Well, we care because in practice, if you wanted to actually solve this problem, you would estimate V by sort of looking over a class of neural networks and maybe minimizing some kind of MLE, maximum likelihood estimation objective. Well, amongst other things, we know that our ability to approximate a target function, in this case this velocity field, over a bounded, of a class of neural networks with bounded parameters, things like sparsity, maximum infinity norms of the layers, width, so on, will depend on that quantity that I showed you. Actually, it's supremum over time, not just its time 1 value. So this is the uniform in time Lipschitz constant of this function. There are a few references if you're interested in chasing this down. And in addition, if we approximate V by some V hat, which is reasonably close, then all of the bounds that we have that tells us, oh, how close is our estimated density nu hat that is derived from V hat to the true density nu, all of that stuff also depends, the constants depend most of the time exponentially on this uniform Lipschitz constant. And again, a bunch of references if you wanna trace this down. So if for a moment I've convinced you that dynamic transport is a way to do sampling, and that high Lipschitz values of this velocity is generally pretty pathological from an approximation theory and distribution, neural network approximation, distribution, and distribution approximation error perspective, then a natural thing to do is to say, okay, within some class of velocities that depend on tau in some way that I'll show you in a minute, find me the tau that is going to make this quantity as small as possible. Why? Because a more regular velocity field is nicer in the ways that I just told you. Okay, let the class of admissible things be C1 and whatever, have the regularity that we need. The boundary conditions are for consistency, so that transport actually occurs. And for the purposes of this work, we assume that we have access to some T that pushes forward mu to nu. This can be whatever it wants, as long as this condition is satisfied. And we consider this data of the problem. And in addition, we specify that the class of flows and associated velocities will have this form. So flows will be this affine, will have this affine form I showed you, and the velocity there is what's needed for the original ODE to be satisfied, right? Geometrically, this is a very simple thing. Just go from x to t of x on an array with the rate specified by tau. Okay. Why is this sort of an optimization problem? Is because you have to cover unit interval in a unit time. So if you go very slow at some point, you have to go very fast at another point to compensate in your trajectory. Cool. Remarkably, there is a closed form solution to this problem that you can write down. And for certain constants that depend on the spectrum of the Jacobian of t, in fact, they depend on the uniformly largest and uniformly smallest eigenvalue of the Jacobian of t, the optimal schedule, or n optimal schedule, has this form. Okay, what does this mean? The constants here are very explicit. I mean, they're ugly, but we know them. So I'm just putting them there for you guys to see them. But all of this is saying is that the optimal thing to do is to do a sigmoid in time. So what is it saying? It's saying slow down at the beginning and slow down at the end by some amount, and to compensate, speed up in the middle. It's possible that only one of these branches exists of the sigmoid. This T0 parameter, for example, is the inflection point, and then the other, like the alphas and the betas, determine the curvature. But why is this intuitive, right? Well, this is intuitive because in this problem, there are two types of pathologies. When you're starting off traveling on the ray, there can be sort of a corner forming at the beginning of the transport. When, look at the left, this is the uniform schedule in time. When things that are like far apart need to go to land at different modes, for example, there's going to be a corner that's going to form in space. That's going to contribute a high value in the derivative of your velocity field, right? Because it abruptly changes from one direction to the other. And the other possible pathology is that at the end, things that were far apart come very close together. If they're traveling with a fixed speed and a fixed direction, this is again going to create the same problem. Like there's a very high change in velocity in a small amount of space. So exactly these two things are the two things that the schedule is trying to compensate for. It's trying to slow things down at the beginning to tamper that singularity and slow things down at the end to tamper that singularity by like a quantitative amount that is specified by those constants that I showed you. And that's sort of what it looks like if you plug in the optimal schedule into the trajectory. It really smoothens it out. Quantitatively, it reduces it exponentially. So if sigma star max and sigma star min are the largest and smallest eigenvalues uniformly over spacetime, then under the trivial thing, you would have something that goes as the max of the largest guy and 1 over the smallest guy, but now you made it exponential in the product of the two, or the ratio. Or, sorry, logarithmic. A few words about the proof, because I'm running out of time. The first thing to do, which is not that hard, is to reformulate this in terms of a more explicit objective as the max of the L infinities of two functions that are evaluated point-wise on tau and tau dot. And this is just remembering that the Lipschitz is the operator norm of the gradient and just doing some algebra, nothing too subtle going on. But then the next thing was, staring at this optimization problem over infinitely many dimensions. I come from a physics background, so I wanted to find the Lagrangian somewhere and apply Euler-Lagrange method. So I said, okay, why not replace L infinity by LP? So then this becomes an integral of some stuff. You can call that stuff your Lagrangian, and you can apply the direct method in the calculus of variations, also known as Euler-Lagrange method, to derive an ODE for the optimal schedule, and then you solve that ODE and you get the formula. Why does this make sense to do? This is the technical crux of the paper, and unfortunately I don't have time to explain to you how we do it, but the whole difficulty is to show that if you solve all of these relaxed problems, in some sense, their limit is going to be a solution for the problem you wanted to solve in the first place. And the right sense here is cluster points in L2. And the way to do this, the way to solve this is by using this beautiful theory from functional analysis, the theory of gamma convergence, which exactly answers questions along those lines of when are limits of minimizers in a very, very general sense, in an arbitrary topological space. And there's a subtlety here, choosing the right topology and so on. But unfortunately, I need to wrap up. So just to tell you what we did, we formulated the optimal scheduling problem. We developed a variational approach to solve it. We used gamma convergence and the direct method to do so. We derived an explicit expression for a minimizer, which I showed you. And then we noted that under this minimizer, the optimal value decreases exponentially. So with that, thank you very much. And yeah, let me know. These are the references.
Any questions? Okay, I have a question. So can you bring up your figures again, showing the one on the left and the one?
Second figures or the first?
I guess the second one. Yeah. So here I wanted to understand the distributions you're moving between are Gaussian mixtures. Yeah. So what I was trying to understand is, at time t equals 1, it looks like you have bounded support. Like you have two. Is the distribution not supported on two intervals? Like
no, I just think we're not plotting the tails.
Okay.
Because yeah,
So like
one
I see.
of the mass.
Right. I see. So like where let's look at the blue diagram. You have these two blue polygons that kind of separate from each other. And so in between, there's mass that is going to fill in the region between the two intervals. Yeah, okay. Okay, I see. And it has like unbounded support going off. Yeah. Okay, all right, that makes sense. I see. So you're just showing like the majority of the mass.
Yes,
how
that's still are enough to generate a singularity.
Yeah, okay, interesting. All right, thanks. Any further questions? All right, well, this is the last talk of the session, but there are closing remarks over in the auditorium, I think maybe starting in 10 minutes or so we can make our way over there. And let's thank the speaker one more time.